Got it. Okay. All right. As usual, we need to activate our Google Earth Engine account. So where is my code? Gmap, to the examples, the notebooks. 108. No, 118. But it shouldn't matter. Here. Oh, it's alive. So make sure your Google Earth Engine the passcode is updated. Okay. Now I have to go to our example, which is neither of these.
I think it's machine learning.
Yes, machine learning applications. Oh, we're in step 4. Creating soil maps. So let's recapitulate what we did last time. Implementing a linear regression algorithm. What we did here is that I had my points where I sample data. It could be level of contaminant of, it could be measurements of biomass. It could be the level of greenness of turfgrass. So, but I have a value related to coordinates. And this could be for a single day. It could be for multiple days. Like every week I go and collect data. So that was a step. So I have the data and I went to the field on the days that the satellite was passing over. So I have, for my reading, I have also an image at the same time. Certain variables, you have more leverage. Like let's say, I can collect the data yesterday, and the satellite is passing today. That is more feasible for leaf area, like biomass measurements, variables that don't change too much, or the level of greenness of turfgrass, or if I'm, let's say, I want to classify or I want to classify an image based on different features on the ground, yeah, I have more leverage. But in certain variables like temperature or soil moisture, it has to be the same day. And in temperature, it has to be at the same time. Okay, at the same time. So the Landsat is passing around 11:30 local time. So at that time, you go to the field. Yes. So soil moisture, you can collect it during the day. The value is going to change, but it's not a drastic change. So, but you cannot do it like collect tomorrow soil moisture and relate it with yesterday image. So there has to be a direct correlation. Okay, so I had that data. I detected my satellite images. Notebook number 1 allows me to extract now for every point the pixel values for each of my coordinates and create a table. Not only I created this correlation, no, or this soil moisture value and the surface and temperature data, but also I calculated many vegetation indexes, like 50 of them. And also I have for every point, I have all that data with me. So that's the table I created in step 1. In step 2, okay, in step 2, what I did is I looked to understand that data. When we do any analysis, we always have to understand the behavior of the data. That means how soil moisture relates to the blue band, to the green, to the red, to the thermal, to vegetation, to the NDVI, to the SAVI, to the OSAVI, to the... So that means I have to plot the data. And that's what we do in step 2. Plot the data. So we reorganize our data, so make it more understandable. But then we start plotting. Plotting. And this plotting can be done in Excel. But if I have 50 variables and I want to plot them, all of them at once, coding comes to my help. So what I have here is a loop for any vegetation index in my vegetation list, create a subplot. So I can have that so coding is important. So I see that in my graph, nothing correlates. Nothing correlates linearly. I don't have a clear trend between soil moisture and any of the variables that I'm looking for. Okay, so that was step 2. Step 3 looks to, okay, well, let's try linear regression. Let's try to develop a linear regression and see if there is any correlation. Again, can be done in Excel, sure, because it's just a table. But I have too many variables. This is against one of the variables. This is one of the vegetation indexes. I do a linear regression. I got the intercept and the slope in the equation. This is my linear regression. Not good, right? Not good. Then, what if I try all my variables? I try to do a linear regression with all my variables. Nothing. Also, by this point, I think I have reduced the number of predictors. I had a step, I have an option in step 2 where I look at the correlation between the blue band and the green, the blue band and the red, the blue band and the near infrared. And I found if I find the correlation between these two variables larger than an amount that I consider high, I reject the second variable. Like I keep the blue and I reject the green. I keep the blue, I reject the red. But if the relationship between the blue and the near infrared is lower than my threshold value, I keep it. So from the 50 plus potential variables that I have to do the linear regression, I kept doubling 17. So I reduce the collinearity or the correlation or between the data. That's one way to simplify. Is that the most exhaustive way to do that? No, there are more analysis that you can do to even further reduce that or keep some variables that were eliminated. But this one is very practical. Like you correlate the blue band with the red band. If the correlation, in our case, I assume 95%. If it was 95% of correlation, which is very high or higher, poof. Okay. So step 3 is trying to find a linear regression, one predictor, any of the variables that we say from let's say the purge of the correlated potential variables. And then I use what is called a technique forward variable selection. And this technique was, I have these 17 potential predictors. If I try individually each of them, none of them give me something interesting. What if I try a combination of 2, combination of 3, combination of 4, combination of 5, or combination of 17? So it's really a wonderful tool to find a potential combination, let's say 5 variables or 3 variables that can predict my output, which in this case is soil moisture. So based on this library that we have here is called MLXtent. And I think did I show you the website of MLXtent? MLXtent. is a very robust library for day-to-day data science task. I really enjoy using the model. So it has examples for application of machine learning, for classification, but these are not part of Google Earth Engine, like inside the Google Earth Engine archive. It has to be worked the data outside in your local computer or in HydroShare. But in this case, it has also linear regression capabilities. So I'm using that linear regression to do what is called the forward variable selection, or where is it? The backward variable selection. So the forward means I'm going to test first individually each potential variable. I keep the best. It might not be the greatest. It's not the greatest yet, but it's the best. And then I want to do combination of two, but with the best. That was the first best. I keep the best of the combination of two variables, and then I add a third. Keep the best at the fourth. So this figure, what it's showing is, this is the best combination of one predictor, the best combination of two predictors, the best, up to 17. And this is the mean square, negative mean square error.
Negative mean square error.
Yes, I think I put that. It is negative mean square error. That's so the closer to zero, the best.
What is the equation? I know that
The root mean square error
and then there's
to the power of 2. To the power of 2.
What is the negative x multiplied
by minus 1? So you see that one variable gets me up to here. I'm trying to get to 0. So I get 0 when I use 5 inputs. After that is constant. And I start adding the last variables, it starts performing bad. So this combination of 5 variables, 6, 7, and 8, give me the same performance. What I want is the simplest model, the model that has the less variables. So in this case, it's 5. And the technique tells me the name of these variables. Band 4, band 5, temperature, and a couple of vegetation indexes. Cool. Then I have the backward variable selection, which instead of doing from 1, the best of 1, the best of 2, the best of 3, the best of 17, and then start eliminating 1, the best of 16, the best of 15. So it goes from here up to here.
The reason you got the same result
is I don't get the same results. The variables that I had, keep in your memory these variables, okay? Band 4, this is for the forward, 4, 5, 6. This vegetation and this vegetation, okay? These are the results for the backward variable selection. So the only one that is similar is band 6. Why? Why I had 2 results?
Yeah, because I think the method should be one.
Oh, it's because the true method to solve it is a factorial.
Yeah, okay.
This one is a lower subsetting of that potential factorial solution. So imagine you do all the combinations of 1 or all the potential 1s and then all the potential of 2, but all the variables. So it's like you have combination of 2 of 17. Remember that C, and then you have that 2 of 17. Then on top of that, now you do all combination of 3 of 17, all combination. So that number is probably 1,000,000 runs.
Exactly.
This is not 1,000,000 runs. This probably is less than 200 runs in the forward. So because in every iteration, we pick up 1 and we keep it constant, right? In the forward, we do the first loop, we keep the best. Therefore, we keep the best. We're eliminating all the other 16 potential combinations. So our subset already is decreasing. When we do the 2, also we're fixing 2 and eliminate all the other possible 15 potential combination of 2. So we keep decreasing that.
So when consider 2 is try to like consider different way that they can combination of 2 variables and then calculate the performance.
So let's say we have only 5 potential variables,
Yeah.
right? Okay, B1, B2, B3, B4, B5. Okay.
Okay.
Okay. Tell me what are all the combinations
Of
of 1 or 5? What's this number? 5. What's all the combination of 2 from 5? So I have to do this. 1, 2, 3, 4. Okay. 1, 2, 3, 1, and 2. 4, 3, 2. Okay, this is 9. Okay. Now, but when we do this methodology, the forward, we're saying, let's say 2 is the winner of the first round. Give me the best statistic. Okay, so I'm eliminating all of this. I'm eliminating all of this, and I'm just going to do B2, in this case, B2 versus B1, okay? B2 versus B3, B2 versus B4. So I have 1, 2, 3, and 4. So I have my 5 and 4. So I don't do 9 now, I do 4. So when you try to do 3 or 5, now you have to do 1, 2, 3, 1, 2, 4, 1, 2, 5. But if I already fixing a best predictor in every iteration, I'm reducing this number. The first one is the same, but the second start reducing by almost half of it.
So for 3, using 2 of them that fixed in the previous step and go forward.
Yeah, so when I want to do this, I'm going to fix 2. So how many combinations of 3 with these 2 I can do? So I can do these. So these ones are fixed. So I can do these ones plus this
2,
one,
3.
well, this one, and this one. I have 3. So this, the forward variable selection, is a subset of the full solution of all potential combinations. This will be the solution will be a full factorial.
So in the backward, try to remove the one has
Yes.
4, and the one is
That
4.
lowers, yes.
Okay.
So in the backward is the opposite. What I want to do, I have B1, B2, B3, B4, B5, and I'm going to do
5 by 5.
first. I do this, the combination of 5 over 5. That is just 1, right?
Yes.
This is the last, or to give you an example, is this one. Then I'm going to do, what are the combination of 4 out of 5? I could have 1, 2, 3, 4, 1, 1, 2, 3, 5, 1, 1, 2, 3, 4, 1, 2, 3, 5. I can have 1, 5, 4. So I do, how many combinations I do?
The equation is.
There is an equation, right?
Yeah, but the equation.
Yeah, but this something like that is combination of this, I think it was, is A minus A, no, that's not right.
Divided to something like that.
Yeah,
So is 4 factorial divided to 5 minus 4
4 factorials
divided
minus
to
divided
yeah
by,
5 minus 4 factorial
okay,
multiplied by 5 4 5
multiply by what?
4 5 in the
4,
yeah in the one
like this?
um,
I do remember the first
should
part.
be
yeah.
here.
Huh?
Six.
Oh, oh yeah, the bottom
No,
multiplied by the 4. By the
Okay.
4?
Yeah,
No, it shouldn't be the 4. It can cancel quickly.
It's 1 should be 1 factorial. Yeah, it doesn't work.
I think it is
It's 4.
4 factorial, or well, it's 5 factorial on top,
Okay.
but it's 4 factorial on bottom.
Oh, okay.
Yeah, sorry, it's
Okay.
5. Yeah,
All
that's
right. Okay.
yeah.
Now it makes sense.
So there's
So,
5 combinations.
so you have, yeah.
Yeah, that's works.
So this solution is 5 by 4 by 3 by 2 by 1 over 1 factorial times
Plus 4
4,
factorial can
3,
bring all of
2,
those.
1, 5.
Yeah.
Okay. So when I do the backward, I do this, but now, because I did all these 5 combinations, I'm going to choose the combination 4 that give me the best. And then I am going to do 5, 5. Now I'm going to do all combination of 3 out of the 5, but with one variable
One of us
is constant.
Constant.
Yeah, but so now I'm going to do all combination 3, but I'm going to force one of them to be constant.
One also has prompt. How about the first step?
Sorry,
Combination 5 of
No.
1.
here, no, I think here I have 4, but here I found a combination of bands, let's say this one, this one, this one, and this one are my best second. Okay, so now I reject this one. I don't need variable 3 anymore, so I need to find now the best combination of 3 out of 4. Remember this variable, now that I'm moving that way.
Backward.
Yeah.
Sorry.
So no, that. So I keep eliminating variables until I reach 1. But how I'm going to choose? I'm going to choose looking forward the one that gives me the best. So what is telling you in the full factorial solution, there are multiple solutions that can give you the same answer. Multiple combination of inputs. So when we do statistics and we are taught statistics, we are not taught how to do that full factorial because the number It's huge. Okay, it's too huge. What will be the full solution? All possible combinations.
Like 5 and 1, or
Five.
So
and
if
five
I have
factorial.
5 variables, all the ones, all the combination of 2s, all the combination of 3s, all the combination of 4s. There is an equation to
should
find.
be, yeah. I don't know, it's like.
so it'd
Five
go
factorial.
1, 5, 10, and then it'd be 1, 5, 10. Let's see. Wait, 5 and 2. It's also, wait, 5 and 3 would be 10, but 5 and 2 is also. Okay, 1, 5, 10, 10. And then 5. So
1, 5, 10, 10, 5, 1. So it has to
5.
start 5.
Okay.
5, because that's the first solution. All the combination of 2 shouldn't be 9.
Oh, sorry, I was doing the back. I thought I was doing
Oh, the
5,
back.
4.
Oh, the backward.
Okay, 5.
Okay.
1 plus.
No, if you,
5.
the backward is a subset. Every
Okay,
iteration
yeah,
keeps eliminating 1.
Right.
But if you try to do the full factorial, not forward, not backward, but every potential combination of ones or
Is not
2
n
variables
factorial?
Huh?
Is not n factorial?
is kind of a factorial. Is like it's a combination of, you have n, but here you have from 1 to n. So this number is large. So as you try to iterate, which is possible, the ML extent can do the full factorial. But for small numbers like 5 variables, that's fine. But for 17, we'll stay all morning here waiting for the results because it's a full factorial. But on that full factorial, you are bound to find what we call it the optimal solution. The forward variable and the backward variable selection are finding suboptimal solutions. Like, probably you have seen this concept that you have x and you have fx, and you have seen this formulation before. This point, let's say if I'm calculating this, the negative root mean square error, this is the optimal solution. Okay? But the neighbors are suboptimal solutions. So these ones are the forward and the backward variable selection. To find this one, you have to do the full factorial. So if the number of variables that you need to put into the model is small enough, like 5, yeah, there is no reason to avoid the full factorial. But if the number is large, let's say instead of 17, I still have my 50 variables. A full factorial of 50, it will be a week of running. So I'd rather use a trick to approximate a suboptimal solution. Well, suboptimal sounds bad. It's called near optimal solution. It's not perfect, but it lowers enough or reduces, in this case, my amount of error with the less computational effort, with a small computational effort compared to the full factorial. So that's what goes into that 2 examples of the linear regression. And this is, you know, who use these techniques? Economist people. Okay. We computer science, we can put, or we engineer, we can put together computers and say, okay, I'm going to run a subset of the full factorial here, 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 here. Nobody enters to this room for 3 days, okay? And I'll be collecting the data, sure. Yes, but economists always try to slash and try to make the model more simple and simple. So these techniques were developed to find a closer, not perfect, but the closest solution to the perfect solution. And it works in our case. It works because we have a lot of variables that stay after our purge of correlated variables. So now in step 4, how good is our map? So by looking at the results of step 3, this is my scatter plot between the results of the forward variable selection and the true soil moisture values. Not bad compared to all the individual vegetation in the soil moisture. I have here a line.
Yeah,
Okay. And I have, this is my coefficients for my linear equation. So I know how much weight every variable brings to the equation. So if you remember statistics, I mean, if you remember statistics, if you have an equation like this, and this is again from my statistic class, you have A1 x1 plus A2 x2 plus B. Okay, if you have an equation like this, if you do this, y over y plus A2 x2 y plus B over y. Basically, this is 1, right? And all of these have become, now is A over y here. Sorry. Yes. All these coefficients, now the sum, what was it? The coefficients are okay, but the coefficients, I remember the sum of the coefficients or the sum of the inputs. The sum of the, if you do this division, then all of these become percentages. Because everything has to sum to 1. So you can now see the contribution of every section to the major equation. So this is what economists uses to say, oh, we need to solve, let's say, we need to improve the socioeconomic conditions of West Valley, Salt Lake City. Okay, what are the variables? Security, services, they give it weight.
Sensitive analysis. Which one is more sensitive?
What is more sensitive to it? So now we have these coefficients and we can use now those tools to look to interpret this if we want. It's not our goal. Our goal is to produce a map.
Yeah.
So, but we can now bring that in machine learning. We don't know the behavior of this coefficient. These are not linear. We cannot see that equation. But here in linear regression, we do. So this is the forward variable selection. And this is the backward, sorry, academic, you should say backward. This should be the backward variable selection. It's a slightly different. This one versus this one. All of them are linear solutions. Yeah. So basically we have 2 winners, 2 potential solutions.
So here you cannot choose one.
You can keep both. Look at us, and this is another thing. How many? Does any of you have played with the OpenET data? Look at the website. Wander around the OpenET data. Let's go to OpenET. OpenET is ET data. OpenET data is a platform that gives you evapotranspiration data, but let's go to Logan, Utah. Okay, this is the golf course, this is the water lab. Around here is where Masmet goes to meet with her advisor. Okay, so let me see the raster view. So this is the quad. What it shows me is the variation of water use in the quad monthly per year, but it's telling me this is an ensemble. This is not one model, this is multiple models. If I want to see all the models, I have to click each of them. My question for you, which one is better? Which one is the true or the most close, the closest to true?
Say in case if we don't have ground truth data, but then we have the ground truth data.
Yeah, because right now I have two solutions for the soil moisture. I have one from the forward, one from the backward technique. Both of them seems decent. So
and maybe in some case one of them works better, in another case.
Yeah. So what we need to do now is to see how that soil moisture data works. Okay. Because here we see that some models give you lower values, other models give you higher value. OpenET is not telling you use one or use the other. Hey, here is all the options, you choose. And how we choose? Well, we need to do extra validation, which in our case, we don't have extra points. But what I'm trying to, my point here is that OpenET is saying this is the absolute true model. There is no other model in the world that can. No, here are 5 models, well-respected models in the ET research community. We won't tell you which one you should use. We are offering you the data for all 5. So in our case, we have 2 models, right? And the next step will be to have more soil moisture data and check if the map results work. But we just had so much small soil moisture data in this case that we don't have that luxury. So what we're doing now is in step 4 is to see the map. So as usual, we'll open the console. I just sent that tweet to the EEMON developer. It told me that it can work for drone data too, like generating all those 50 vegetation indexes for our Landsat image. He says that his code will work for drone data too. So imagine 50 layers of image for your drone data. That will be something. So that's something I want to do in the summer. So, okay, let me see. Do I have my images? No. Let's have images here. Okay. All right. Where is it? Okay. So I have my area, which is the delta area. Let's see. Where is my? Oh yeah, I haven't set map. Now, here is my Landsat image collection. But now I'm going to tell the Landsat image collection, give me only, so I have the forward variable selection requires band 3, band 4, band 6, and 2 vegetation indexes. So I'm asking here those vegetation indexes because I already have the band 6, band 4 in the Landsat catalog. So then I am going to read in the previous step, I save the coefficients of my linear equation in a CSV file, and I'm calling it. So I just have numbers and I have Google Earth Engine, Google Earth Engine images. So now I can do this, and this is called image regression. So I'm going to write an expression, which is, I have coefficients, but I have the name of the bands in the equation. And for every term of the band, I'm going to say image select band 4, band 5, band 6, the vegetation index that I wanted, the other vegetation index that I wanted, and to the result, name it soil moisture. This is a function. This is, so because I have the entire archive, I can apply to every image this function and have like a time series soil moisture now. Now, I created a function and I'm going to apply it to my image collection of Landsat. And why it didn't run?
I think you didn't run the line.
Oh, did it? Okay. Okay. Okay, I'm going to select now the images that I use for my study. And now I'm going to plot it. What I implemented in this function is the forward variable selection soil moisture. I'm using these coefficients. You can see that up to the last number is copied there in that expression. For this, for the, I try to do what's called a time series, but with the clouds, it doesn't look too nice. So here is the map. So you already know the drill here. I have is classify everything. I had soil moisture for only the agricultural area, but this is classified fallow areas, the reservoir, the river, the shoreline around the river. What do you think? Do you think is let's see the scale. My scale is going from legend colors. I'm going from lower soil moisture is orange, the higher it goes yellow, green, cyan, and blue. Blue is 0.6 cubic meter over cubic meter of water. So if it's 0.6, if you have soil moisture of 0.6, this is pretty much water. This is saturation in soil moisture. So if I'm in the blue, okay, I'm in saturation already. So, and the soil moisture cubic meter over cubic meter, this is very dry soil. So these are my extreme values from the orange color to the blue color. With that information, what do you think about my map? What do you think about the reservoir? The blue, this. Not bad.
Yeah.
Not bad at all. Then let's get closer to the fields. So what are, because I did this regression for every individual pixel has its own value. But you can see this field. What do you think about this field? What's happening there? Look at the reservoir and now look at the fields. What do you think has happened in those fields?
It's recently irrigated.
Just irrigated.
Yeah.
Yes. So we can detect now fields that were irrigated recently because the soil moisture is very high. So we see very clearly which fields. What can we say about this field?
Maybe several days ago it's irrigated.
Yeah, 3 days ago, a week ago. And what can we tell about these fields?
They just should irrigate it very soon.
Okay, they are closer to this lower stage. Now I know that these probably the next fields to be irrigated are probably going to be these ones because they're dry. So now I have my map of soil moisture.
Center pivots is really cool.
Oh, let me show you this the center pivot. Yeah, that's a good point. There is a center pivot here. Look at the center pivot. Oh, yes, this one. Tell me what's happening in this center pivot.
Oh, yeah.
Look at this. Tell me what's happening here.
It looks like the sprinkler like got to this point.
Distribution of the irrigation.
It's moving like this. No, it's moving like this. This is where the center pivot is. This is past, let's say 1 or 2 days back, and this is today. You are seeing the rotation of the center pivot as it is irrigating.
That's cool.
So
And also the distribution of the.
you can see that this, yeah, and in center pivot because they rotate, like one rotation could be 4 days. So you cannot judge like the distribution used based on one image.
Minimum like.
Yeah, but yeah, center pivot here, center pivot. These are dry. Look at this one has a. Let's look at the other ones.
There's a whole cluster of center pivots like right in the center of the map
Uh-huh.
that have really good resolution.
Oh yeah, that's Holden, I think. Where is it? So I didn't clip it. I did it for the entire Landsat image. So what are the assumptions? That's a good point. It's also doing forest areas. Was my data collected in forest areas? No, it was collected only on the agricultural land. So whatever estimation my Landsat image is doing here could be not. So use as a guidance, and that's the thing. We always have to be honest from which sort of environment that data came from. It didn't come from the forest areas. It doesn't represent it. The data doesn't represent. This is a lake, or this is a reservoir. So these areas, we didn't have data, but these areas here, this is fallow land. We are having low values. It's expected. They are not irrigated, right? So we're having, but also I didn't have data there. But it seems, and that's what we will say if we write a report, it seems that the data contained in our samples can help describing the fallow land conditions. It will be recommended that in additional data collections, some soil moisture sample collection will happen in the fallow. So we will never make the claim, oh, it works for fallow land. We have to have evidence to demonstrate, like we have samples in the fallow land and our samples match. No, what we're seeing is that, yeah, we expect this to be dry, okay, but we don't have data. But the image seems to be correct. So we say it seems to be working, or it seems that the algorithm can describe fallow land conditions. And here, yes, here the soils might be shallow, there might be exposed rocks, there are trees. So here we have very low confidence that this measurement, this is the mountain range that crosses Utah, we have a low confidence that these values are correct. Here, center pivots. You can see the movement of the center pivot. You can see where the arm of the pivot is.
So are we getting close to the point where like these center pivots or like sprinkling systems could be like receive inputs from satellite imagery and know when to go, when to stop, just based on like?
Yes, we are very, very close. What need to be solved for that, here is the last image. Okay. Well, the last image of the forward variable selection. So to do that, we have to solve this equation. Ray plus ET plus irrigation plus minus runoff minus deep percolation. This is water that will infiltrate beyond the root zone. Okay. To control the center pivots, this is the value you want, the amount of irrigation. So that means we have to have so assuming that you're going to do, no, you're not going to extra irrigate. Assuming you are not going to flood your field, assuming you're not. This, we saw maps, and you can put a weather station that sends the data to the cloud. So we have this data. OpenET. Now the issue is which of the 5 models you want to use. Okay, but now it's available. This is still. So we're one step away to truly solve this one. And that's why there are many researchers in the planet trying to solve it. You solve it doing linear regression, okay, and Landsat image, and you have 2 solutions. Okay, so it is possible, but the 80 points that we had for this exercise are not enough. This model, we will need more records, more years, more crops, more variety. So
more variety.
Like I would say 500 samples to have over 3 years of data collection. This is just 4 days of data collection.
How many?
Yeah.
4 days.
Yeah, just 4 days.
Points? How many locations?
20 locations.
20.
So for this data you have here, like, because I know like the Hydroblocks SMAP data is like 5 centimeters of penetration, but this
was this is also 5 centimeters.
centimeters.
Yeah.
Okay.
So that's the other issue. we need this for the root zone. That means we need to do it from the surface up to 3 feet or 6 feet. When we solve this, then this is solved.
Plus that can help us like for the depths, like
There, I think previous students have pushed this to 1 meter. There is another researcher. There's another researcher that is using like OpenET data and radar data, and he's able to do it also 1 meter. So we're getting very, but the model is horrendously complex. Okay? It is not a model that you will, like in this case, we prepare every input, right? And we add to the map. No, this one is a model that, like OpenET, you just have a platform to access the data. It will be very hard to implement. So he's building a sort of OpenET, but for soil moisture. But look, we are very close. We have rainfall from weather stations or raster data. ET from images. This was, it depends on the management, okay? So this one, we can operate those center pivots from a computer.
That's cool.
Yes. Yeah, we're like this of close 5 more years, and probably myself with less hair will say, yes, solve it. Yeah, your homework is to calculate this, right?
Yeah.
Your homework is the example will be, oh, I collect 80 points. No, now download OpenET data, download the hydroblocks and do this for tomorrow, something like this. It will be different, but we are extremely close now. So again, if you keep running the code,
this one for what?
this is for backward. So this is my example of a term project for you, okay?
Very nice.
Okay. To show you that, okay, we have worked pieces of what can be done, but I'm showing you, okay, put it here, combine it with this one, put the colors, put some of your knowledge of reflectance and regression and statistics all together, and we got an example like this. So you cannot complain that your advisor never did the homework by himself. Okay, I did. Okay, there you go. This is showing. I mean, I do like this rotation. Look,
Yeah.
this is telling me the model is representing actual behavior of soil moisture. See this rotation, this increase in soil moisture here and lower here is telling me, yes, the model is doing its job. I can have more confidence after examining the data that the model is working. Linear regression model. The original source of this, I did a machine learning model. It took me a year to do that, to develop that. But now it's just an exercise with just more clever approaches, this forward variable selection and additional inputs. We're using vegetation indexes we never seen, right? But this statistical model say, hey, use this and you can approximate your soil moisture. So sometimes machine learning, we go to machine learning because it's our lack of knowledge. That let's say we know use NDVI and SAVI and basic, but if we were able to put all the creativity on transformation of the reflectance data, we can get a much simpler solution. And this is an example of that. Oh, here I have a bar. So now you have access to my code. You can plot, you can ask me questions about it. And but it works. And I was so happy to do this. Fun? Fun. All right, I hope you enjoy it. All right. All right. Well, that's it. That's the end. Oh, there is one more, and I'm just going to refer it because I have only 80 points. Is the solution, step 5, is trying to implement a machine learning, but based on those few points. I know it's not going to work. In machine learning, you have to have 500 points, 600, 1,000. The most modern machine learning use 10,000 samples. Okay, so that means collecting data, teams of California, Utah, New Mexico, Wyoming, all of them streaming your data or organic the data for you. So it's possible. There are now efforts, but I don't have it. Like, so what I did is, okay, I'm going to try to do one model, call it. Yes, so here I'm going to install what is called the relevance vector machine. And this is a library in Python because with little data, the results are not satisfying. Here are my points where I collected the data, these 4 visits to the site. I have my data here. Oh yeah, I'm here. I think I'm getting soil moisture data. Here I'm just organizing my data. And I have my geometry, my coordinates, my soil moisture. So instead of going the exercise of collecting all the 50 vegetation indexes, I'm just going to use the ones that I saw in step 2 that are important, the 17 variables that we use at the end. Then here is where I tell, hey, I have the soil moisture for this position. Give me the pixel value for that location, but keep it in Google Earth Engine. But this was something that Masumet was asking me the other day. So this is the solution of your question. I have many points in a shapefile. How do I extract the information for all those points? This step 5 is the one that does that job.
It was my question.
Yes, so here, for example, I have many points. That's the coordinates, and here are all the pixel values for that location. Then I keep doing my transformation of the data. Yeah, so if you want to use Google Earth Engine for your project, this is the notebook you want to look at.
Yeah, because I was working on it.
Yeah, this is the one that solved it. Okay. After a lot of cleaning, so here I'm summarizing what I explained step by step in the previous, but now doing it in a single notebook. Okay, now I'm collecting training, testing data as we did for classification. And here is where it comes, the training testing data. Remember, you use random forest, leaf, and support vector machine for your classification. I'm going to use I think I'm going to use leaves to do regression. So here is, this is the same code as you use it. The only difference is that I'm saying the default is classification, but hey, give me regression. I want values from 0.1 to 0.6. And here comes the map. It's not that good. So I tried also random forest. Forgot I tried random forest.
80 points.
Too little, too small sample for that.
Yeah, because soil moisture is really kind of variable, so very.
I think there is a way to connect the forward variable selection with the machine learning, like the technique that we use to reduce the inputs. But to do that, the forward will have to be inside Google Earth Engine. So Google Earth Engine is not too friendly with variables. So look, I got a map. Okay. I got a map. Let's look at the fallow areas. What do you think? It says that the fallow areas are wetter than my center pivots. Is it right? I don't need to do a statistic analysis to say this is off. It's not, this machine learning is not working. And I can blame the subset. Two little points. 3 is random forest. Okay, let's see random forest now. Same palette of colors to the breadth, the minimum and the maximum. Use as you did it on your classification task. Okay. You can keep running this notebook. I didn't have to code anything or change anything. So it works. What I'm going to do is use a minor update on the text. Okay. Again, let's see. What do you think? This is random forest. Nope. The fallow area is showing wet. Support vector machines.
How about the points that we have ground truth data?
So
more accurate that the regression.
no, did I include that? Did I did a scatter plot? I should do that. I should do a scatter plot on like we did for that. I should include that. But after seeing those images, I was disheartened. This is the support vector machine. No, it's running the support vector machine. So it's not doing a good job. And I don't like, I'm giving it too little data to train the model. More data?
Maybe scatter data is more accurate than variation, is not.
The what?
About the ground truth data, that place that you have the ground truth
Uh-huh.
data, maybe random forest is accurate.
Yeah, but it's not that robust.
Yeah, it is not.
Yeah, it could be good, but it should be able to. Here, look, this is soil support vector matching. I don't see anything. You just give me a constant value all across. So all it's, and I try to find the best number of trees, the gamma value to, but no, I couldn't find anything that improved those models. But I should add that scatter plot to show that the model is not working. But that's it. And I hope you enjoy it and you learned something new. All right. Well, that's it for the lectures.